going to wait to see if streaming, as always. I think I'm gonna stay for 1 hour and a half today. And I'm going to try to explain, because I still don't understand well enough, the extended Euclidean algorithm. I spent the whole day yesterday. I wrote a bunch of extra stuff, and I kind of get it now a lot more than I did the first time, but it's still very confusing to me. So I'm gonna try to explain the best that I can. But first, I think I'm gonna do this Italian thing here, just to not lose the habit. And I think I'm gonna stay 1 hour and a half today. I might come back later, but probably will stay just 1 hour and a half. I was thinking about it today as well, that I kind of stopped making videos for the other channel because I'm focusing on the blog. But I think that I want to start making videos again, and I think a good strategy is going to be to take the posts from the blog and then review them again and create an outline for a video, and then transform each blog post into a video and post it on the other channel. And it has been a long time since I haven't posted anything there. So I think I'm gonna do that soon, but I wanna have more content on the blog first. Ideally, would be able to finish all the algorithm section and then this initial section on blockchain, which I think is gonna take a lot of time because these things are really hard because I'm not familiar with a lot of them to study. So like this extended Euclidean algorithm, I think is a great example of that, where I thought I was gonna be able to finish at least 2 articles yesterday, but then like there's nothing I can do about it because it's just hard to understand because I'm not familiar with those things. And so let's do this now.
Fa,
Fa,
Does.
fisso,
fisso,
Set. Unchanging.
3,
3,
3.
desiderare,
desiderare,
Desire.
aria,
aria,
Air.
bene,
bene,
Well.
anche,
anche,
Also.
giocare,
giocare,
Play.
piccolo,
piccolo,
Small.
fine,
fine,
End.
mettere,
mettere,
Put.
casa,
casa,
Home.
leggere,
leggere,
Read.
mano,
mano,
Hand.
portare,
portare,
Carry.
grande,
grande,
Large.
compitare,
compitare,
Spell. Words.
aggiungere,
aggiungere,
Add.
anche,
anche,
Even. Also.
terra,
terra,
Land.
qui,
qui,
Here.
devo,
devo,
I must.
grande,
grande,
Big.
alto,
alto,
High. Tall.
tale,
tale,
Such.
seguire,
seguire,
Follow.
atto,
atto,
Enact.
perché,
perché,
Why.
chiedere,
chiedere,
Ask.
maschi,
maschi,
Men.
cambiamento,
cambiamento,
A change.
è andato,
è andato,
He. She went.
luce,
luce,
Light.
tipo,
tipo,
Kind. Of thing.
spento,
spento,
Turned off.
bisogno,
bisogno,
Need.
casa,
casa,
House.
immagine,
immagine,
Image.
provare,
provare,
Try.
noi,
noi,
Us.
di nuovo,
di nuovo,
Again.
animale,
animale,
Animal.
punto,
punto,
Point.
madre,
madre,
Mother.
mondo,
mondo,
World.
vicino,
vicino,
Near.
costruire,
costruire,
Build.
se stesso,
se stesso,
Himself.
terra,
terra,
earth,
padre,
padre.
father,
A lot of these I can tell that I'm already being able to remember. One of the ones that was hard for me was bisogno, I think. And bisogno is equal to need. So now this time I was able to remember. A lot of them are easy to know because they are very similar to Portuguese. So like most of them is pretty intuitive for me. But then some of them like bisogno doesn't have anything to do with the Portuguese version. Yeah. So I broke it down the parts and I studied a lot and used ChatGPT to try to clarify, and I realized some stuff that made it a lot easier to understand. The first thing that I realized is that HM is equal to LM but lagged behind one iteration. So HM starts as 0 here and LM starts as 1. And then at each iteration, HM is going to become the value of LM, and LM is going to become this new value here. So LM becomes NM, or actually becomes NM, which is this value here. And then LM becomes HM. So what it's doing here on this portion with this NM is updating this value of the coefficient. Because LM and HM are supposed to be the coefficients on Bezout's identity, which is like a linear combination that it equals the GCD. But when the GCD equals 1, then is a Bezout's identity, I think. And like what the algorithm is trying to find is the inverse modular. I think I forgot the expression, but is when let's say you have two numbers, 5 and 7. So if you multiply 5 by an arbitrary number like x, and you divide that by 7, the remainder is going to be equal to 1. That's what the algorithm is trying to find. It's trying to find at which x number you have to multiply 5, so that when you divide by 7, you get the remainder of 1. And in this case, the number that is dividing is n here. So it's actually, and this LM would be equivalent to a times x, so the other number times the arbitrary number, and the remainder has to be a 1. And this is equivalent to saying this thing here, where x and y are the coefficients. So in this case, they are equivalent to LM and HM, and a and n are the two numbers that are passing to the algorithm. So a multiplied by an arbitrary number plus n multiplied by an arbitrary number is going to be equal to 1. And what that means in the algorithm is that it's using this LM and HM in order to keep track of these coefficients here on each iteration. So it starts off with this low and high, is low being in the smallest remainder of the division of a by n. And then each iteration, it updates these values here so that it's changing the coefficients based on this updating mechanism. And this is what makes it really hard to understand, because in all of the videos that you see, they talk about this, but it's hard to picture that in this algorithm here. So the way that people explain is that they write a number in relationship to the other number. So let's say, let me see if I can think about an example. So like 15 is equal to, I don't know, 3 times 4 plus 2. Plus 3, actually. Yeah. Oh, actually, this is a better example. So you write the number as like one number times the amount of that the division would go plus the remainder of the division. I can't think about any examples now, but that's what you would do. Then you would write as letters instead. So you have the quotient and the remainder. So other way around. And then you pass these numbers to the left here. So k is going to be equal to this number on the next iteration. Then you're going to have another number here multiplied But this is what is difficult to understand in the videos, because the way that they're explaining is more like this approach here where you're shifting to the left, and then it's hard to think about, like, you're shifting the numbers, you're making each number be equal to the quotient plus the remainder, the quotient times the number plus the remainder, and then you are using that to find how you would compose the quotient in the same way, if that makes sense. So it's kind of like you're pushing each number to the left, and then you're doing the same thing again. But like when you think about mathematics, that's easy, because then you can do the calculations in your head of how the number would be structured like this. And then each time you go to the left until you get to the point where the number is 0 or the number is 1. And then when the number is 0, when you get to the point where the number is 0, it means that the previous iteration, the previous equation of the iteration is the greatest common divisor, which is what you're trying to find, and the Bezout linear equation. So it is the Bezout linear equation, and the result of that is going to be the greatest common divisor. And this is why it's still kind of difficult for me to understand really well, like how that stuff translates into this. But if I just focusing on this algorithm here, I think that is a good explanation, where this here updates the coefficients at each iteration based on this formula here, and this is the quotient, which is going to be based on the amount of times that the remainder of this division can fit on the second number. And these I'm still struggling to understand, but like I was able to figure out that this equation here can actually be rewritten with high mod low, which is, let me see if I can, pretty sure I put it here at some point. Yeah, here. So writing this is the same as writing this thing here. But the reason why it's written this way is because this way is more efficient. And I checked this here. Maybe I'll do more checks, because I just checked with one number, I think. So this is pretty much what you're trying to get for updating the value of new each time. You're trying to get the remainder of high divided by low. And so in the way that ChatGPT describes this is that as being the second smallest greatest common denominator. The second smallest quotient. So in the first iteration, you're getting the smallest quotient, and then on the second iteration, you're getting the second smallest quotient. And this is the equivalent of the way that they describe the algorithms in the video, where you're shifting the numbers to the left. And then in the last iteration is going to be, low is going to be equal to 0, so it's going to break the loop. And whatever the value of the quotient, this would be the value of x here in this equation. This is going to be replaced here, and that's the equivalent of finding that formula of this formula here, where a times x mod n has to be equal to 1. So the remainder of the division has to be equal to 1. The remainder of the division of the quotient that would multiply the number a in the linear equation has to be by n has to be equal to 1. I'm not sure if that's clear, but I still don't fully understand, but I think it's a lot more clear now in my mind how it works. And the other equal signs here are just switching the values of the high and low based on the current quotients. Because high becomes low and low becomes new, which is this high mod low. So it's like you're updating the boundaries each time, because the equation changes, the linear combination changes. based on these factors here. And so hopefully that's clear. I think I'm gonna read this stuff that I did here, and then I'm gonna pass this article to the blog, and then I'm gonna start focusing on the Lagrange interpolation. I'm gonna mark this as done. I think for this maybe not sure. I think while I do the Lagrange, I'm gonna read the articles again from Vitalik. I already read a bunch of them today. Finished watching the Flashbots videos. But I also wanna read the book again, the Ethereum book, the wallet part and the transactions part. So I'm probably gonna do that. And eventually, obviously, it's better to build something. But I think that I need to have a decent amount of articles, I think, on the blog first. And I think after I do have a decent amount of articles, then I'll go back to making more videos instead of writing articles, I think. So that way I'm going to review the same information multiple times. It's gonna solidify that in my mind. Let's unpack the code. What we're trying to find is the value of x such that this equation is true. This equation can also be rewritten as this, which is the identity, Basel's identity, I think. Or something like that, linear Basel's identity, something like that. The point of the extended Euclidean is to find the coefficients of this equation. During the algorithm, we keep track of two sequences of coefficients, L and M, LM and HM, such that this is true. If A is 0, this means that there isn't a number that is going to make the remainder of A divided by n to be equal to 1. In this case, the algorithm returns 0 because the coefficient doesn't exist. So that's the first part here. So I copied the algorithm here and I made it with a couple, or just these numbers. Let me do a couple of more to see if let's do 1,000. I and then I plus plus 40. Let's do 50. It's probably gonna take a long time. Yeah, but see, it's all true here. So here I'm checking to see if this value here is equal to this one. Because I didn't. This is the part that yesterday was really like breaking my mind, because I knew there was some relationship here. Like I was trying to encapsulate this into a concept. But the reason why it was really hard for me to do that is because I didn't know like how to put because this is the quotient here. Then the quotient multiplied by the remainder of this division. And I was trying to figure out like what does that mean? And then this subtracted with high, and it's very confusing to understand. Yeah, but now I know that is the remainder. So R is the quotient and the nu is the remainder. And the linear equation is gonna be the Bezout's identity is gonna be the linear combination of the quotient and the remainder. That's why you have these two values here. So in the left is probably the quotient, updating the quotient based on this, and then on the right is updating the remainder, I think. but I'm not 100% sure if that's the case or not. So this is why I said that I understand how it works now because of this. I get this algorithm, but to translate the algorithm into the concept in my mind of the like visualizing this as in the same way that the videos explain of the equations going to the left and then going the path back, where you change the values of the numbers, not the values, you change the order of the numbers, so that is in another format that is based on the coefficients. Like that thing I don't understand really well yet. And I'm probably not gonna spend a lot of time on this, to be honest, because I think it's not that important. As long as I understand like what I explained here, roughly how it works, I think that's fine. And I also understand like I understand the explanations that the videos give about this, where they talk about, but I don't, the part that is hard for me is not that, is translating that into this code here. Like if I like put myself on a person's shoes that designed this code, I definitely wouldn't come up with the solution. That's the thing. It's hard for me to put myself in the position of this person and then ask myself how I would build that algorithm. And I'm pretty sure I wouldn't design it like this, I think. I'll probably do it in a different way, and it would probably be less efficient. That's the thing that I struggle to understand. Like, why do you do this? Like, how do you come up with this stuff? That's the difficult part, I think. But I assume that it's probably, and also the meaning of these things here, because they must have a meaning. It's probably an acronym for something. Like low and high reminds me of binary search. It probably follows some similar logic, like you're updating the boundaries of the coefficients. Then LM and HM are probably an acronym that has to do with something that I don't know. So I assume that this algorithm, probably this implementation, comes from probably some paper or some research or something like that. And this is another thing that I was trying to think about yesterday when I was like trying to understand how this works. Why people decided to name those things like they are there. So on this line, low is always going to be lower than high because by definition the remainder of a divided by n will always have to be lower than n itself. So yeah, and this is like, after I thought about it, it's kind of obvious, but it wasn't obvious for me at first. But if the remainder wasn't smaller than n, then that would mean that n fits more times on a. So it means that it's not the remainder. So by definition, the remainder has to be smaller than the number you're dividing by. Otherwise, it wouldn't be the remainder. So this is, I'm explaining this here. And then I'm explaining that if you use integer division, it's gonna round down to the full int, and so it always goes down regardless of the value. Because in mathematics, usually when you have greater than 0.5, then you round up, but if you use this division, it always rounds down. Is used to update the value of LM in such a way that the linear combination of a and n still adds up to the current value of the remainder. The value of nm is going to be, let me see. I think it's the quotient, maybe. Not sure about this part. It's used to update the value of LM in such a way that the linear combination of adds up to the current value. No, it's current value of the remainder. I think that's correct. The value of LM is going to be the updated coefficient of LM for each iteration, which starts off equal to 1 And each iteration, the value of HM is going to become the previous value of LM. The value of LM is going to become this thing here. So think about this if we are updating LM based on the quotient R of the previous iteration. And HM is the previous value of LM, starting off at 0 in the first iteration. So HM is LM divided by 1 iteration. Here, low represents the current smallest non-zero remainder, and nu will be the next smallest non-zero remainder. So this new value is going to be the updated value of low, which is the updated remainder when you subtract high, which in the first iteration is n by the remainder of the division of a by n, which is low times the amount that this remainder can fit into n itself, r. What you're doing is getting the gap that the remainder has until it reaches n. Another way to look at it is equivalent to nu high mod low. And in practice, the expression nu is used in the algorithm because it is more efficient to compute low times r once and subtract it from high rather than computing high mod low directly. Also don't understand why this is the case, but obviously it has to do with the way that this division is implemented under the hood, but I don't understand, like, it's either, it can be both that and also in the algorithm, the way that it works there, but I don't understand really well why it's more efficient to do it this way. It might be because of the way that the algorithm works here in the loop and how it updates the value of r on each iteration. It might have to do with the operator itself, but I'm not really sure. I think maybe it's because r decreases each time, but then, yeah, it could be that, actually. I don't know. So let's say a equals 5 and n equals 20, then a mod n equals 5, which is the first low, and high would be 20. This means r would be, which is 4. Calculate nu, you would get, which would be 0. New low would be 0 and the new high would be 5. In this case, low would be less than 1, so the algorithm would return lm. Be equal to nm after the first iteration, which would be this, which in this case would be minus 4. This means that minus 4 mod 20 equals 16, and this would be the value the algorithm returns. And this is another interesting thing, that when you have this division on a negative number, what you do is actually subtract the negative number from the other one until it becomes positive. And that's the remainder. I'm not sure how, like, maybe we can test here. Yeah, 15. Because you get 5, you divide it by 2, the remainder is 5, minus 5, and then you subtract minus 5 from 20. Yeah, so you get until the remainder and then you subtract. And this part I just made a slight modification here, but I left the rest pretty much the same. Also the conclusion I changed to be more related to this algorithm here. So I think I think that's, yeah, that's fine. I'm gonna start reviewing the Lagrange interpolation. Mathematics polynomial interpolation is a powerful tool that allows us to find an approximate polynomial function that passes through a set of given data points. There are various techniques for performing polynomial interpolation, but one of the most popular and widely used methods is Lagrange interpolation. Lagrange interpolation, also known as Lagrange's method, is a mathematical technique for finding a polynomial function that passes through a set of n data points. It was first introduced by the French mathematician Joseph Louis Lagrange. Yeah, let's check this out. Lagrange. Probably Wikipedia has this. It doesn't have history here. Yeah, Joseph 795. So then it has been extensively used in various fields such as engineering, physics, finance, and computer graphics. This article will explore the basics of Lagrange interpolation, including its mathematical formulation, algorithmic implementation, applications in real-world scenarios. I think I'm gonna put this stuff here. I think I'm not gonna put this stuff here. The rest parts. One thing I was thinking about is the connection between machine learning and these kinds of things. It seems very related to machine learning, so I wonder if it is used. I don't remember seeing that when I was studying the mathematics there, but I also didn't dive deep into the algorithms. Just like I just studied the surface, let's say. The whole gradient descent thing. It seems like it has a lot to do because it's about finding an approximate polynomial function that passes through a set of given data points. So it's pretty much like machine learning is pretty much that as well. It's actually exactly the same thing. Because the weights and biases are the polynomial that approximates the data points. So I guess the only difference is that it's probably the difference in technique. Understanding polynomial interpolation. Before diving into Lagrange interpolation, let's first understand the basics of polynomial interpolation. Simple terms, polynomial interpolation involves finding a polynomial function that passes through a given set of n data points. Polynomial function can then be used to estimate the value of the function at any other point within the given range. For instance, suppose we have a set of n data points where x and y are the input and output values. Function that passes through this, we can start by assuming that the polynomial has the following form. Let me think about. Oh, there's also something that I think I'm gonna have to read the articles there. Because I remember there is something that they do where they extrapolate the coefficients, I think, for in a list or array in order to make it faster for computing. So there's something about that as well that I need to remember because I want to understand like how they do it. Are and are the unknown coefficients of the polynomial. And then is the degree of the polynomial, the degree. Okay. To determine the coefficients of the polynomial, you need to solve a system of linear equations which can be expressed as follows. So I remember this. I'm not really sure if that's what it's referring to here, but I remember something about linear algebra where you can represent a polynomial based on its coefficients by multiplying like x minus the coefficient, I think, times the other axis. And then if you do it's like you're pretty much, forgot the word in English. And there are other techniques like that where you can, for example, if you multiply x minus 1 times x plus 1, then that would be equal to x to the power of 2 minus 1 to the power of 2. So it can be any letter, obviously. I think like x minus b. I remember some stuff about this that I learned a long time ago. And this would be x 2 plus b 2. Something like that. So it's similar to this, where you can represent like a polynomial, a very big polynomial, in this format where you're just multiplying x minus the roots, let's say. So because this is to find where it crosses the x axis. At which point y is going to be 0, which is the point that the polynomial crosses 0. But I'm not really sure if it's related to this stuff. It's probably one of these techniques that you can represent a polynomial, complex polynomial, in this format here based on some rule that somebody discovered a long time ago. Solving this system of equations involves matrix operations, and it can be computationally intensive for large n. This is where Lagrange interpolation comes into play. Lagrange interpolation provides a simplified approach for finding the coefficients of the polynomial that passes through a given set of data points. The method involves constructing a set of n Lagrange basis polynomials, each of which is a polynomial of degree n minus 1 that equals 1 at one of the data points and 0 at all the other data points. Polynomial of degree n1. I don't understand this. I'm gonna have to research. How can it be 0 on all the other data points? That doesn't make sense to me. The method involves constructing a set of n Lagrange basis polynomials. That equals one of the data points and 0 at all the other data points. Each Lagrange basis polynomial is then multiplied by the corresponding output value yi and added together to obtain the polynomial function that passes through the data points. The interpolation method is computationally efficient and provides an exact solution for the polynomial interpolation problem. algorithmic implementation of Lagrange interpolation. Inputs the set of n data points. It computes the Lagrange basis polynomial. Inputs the products. Step 3, obtain the polynomial function px that passes through the data points. So this I got from Ethereum probably. It's the Lagrange interpolation polynomial for 0. That's going to return p. This is going to be a polynomial. So it's not that hard to understand this one, I think. The only thing that is difficult is because I don't know what x new is. Suppose should be here. But I know that it's constructing the polynomial here by doing the calculation there. By changing the values of L based on the index here. She's gonna, and this is the pattern of the polynomial, I think. Is this thing here. So it's multiplying all of them. Yeah, so this part is essentially this thing here. I think the algorithm is not that hard to understand. I just need to understand more how the interpolation works and what does that stuff this means here. What does it mean to be, for a polynomial, should be equal to 1 on one of the data points and 0 in all the other data points. I think I'm gonna ask ChatGPT.
Edward wearing one. It is also an easy consequence of a formula published in numerical analysis. The Lagrange interpolating polynomial is the unique polynomial of lowest degree that interpolates a given set of data. Given a data set of coordinate pairs with 0 less than or equal to the are called nodes and the are called value. The Lagrange polynomial has degree less than or equal to and assumes each value at the corresponding node equals. Although named after Joseph Louis Lagrange, who published it in 1795, the method was first discovered in 1779 by Edward Waring I. It is also an easy consequence of a formula published in 1783 by Leonard Euler II. Uses of Lagrange polynomials include the Newton-Cotes method of numerical integration and Shamir's secret sharing scheme in cryptography. For equispaced nodes, Lagrange interpolation is susceptible to Runge's phenomenon of large oscillation. Definition edit. Given a set of plus 1 nodes, 0, 1, which must all be distinct, is not equal to, for indices, is not equal to, the Lagrange basis for polynomials of degree less than or equal to, for those nodes is the set of polynomials, 0, 1, each of degree, which take values, equals, 0, if, is not equal to, and, equals, 1. Using the Kronecker delta this can be written, equals, each basis polynomial can be explicitly described by the product. Notice that the numerator, pi, is not equal to, has, roots at the nodes, is not equal to, while the denominator, pi, is not equal to, scales the resulting polynomial so that, equals, the Lagrange interpolating polynomial for those nodes through the corresponding values, 0, 1, is the linear combination. Each basis polynomial has degree, so the sum, has degree, less than or equal to, and it interpolates the data because, equals, sigma, equals, 0, equals, sigma equals 0 equals. The interpolating polynomial is unique. Proof, assume the polynomial of degree less than or equal to interpolates the data. Then the difference is 0 at plus 1. Distinct nodes 0, 1. But the only polynomial of degree less than or equal to with more than roots is the constant 0 function, so equals 0 or equals. Barycentric form edit. Each Lagrange basis polynomial can be rewritten as the product of three parts. A function equals pi. Common to every basis polynomial.
I think I'm gonna try to see if Vitalik has an article about this. And I was reading this one, but I think that it's better to read this one once I start writing or reviewing the article about that. Yeah, I think it doesn't. But he's probably gonna talk about it. I remember seeing on one of these articles. I'm not sure if it's on his site or some of the other sites that I read this stuff. Suppose you have a set of data points and you want to find the polynomial degree n minus 1 that passes through these points. Okay, so n minus 1, it means that the highest number of that x is elevated to is n minus 1. So let's say the points go until 5 here, then it would be n minus 1 would be 4, which means that the polynomial would be x elevated by 4 times a coefficient minus or plus the other x elevated by 3, and then so on until you go to x elevated by 0. If px equals 1 at one of the data points, let's say at x1 and 0 at all the other data points, that p if px equals 1 at one of the data points, and 0 at all of the other data points, this means p1 for i3. I think I get it. So it's 1 for one of the data points in the set here, but 0 for all of the other ones. I thought he was saying that the polynomial that it finds would have to be equal to 0 or to 1 in one value of x and then 0 in the other ones, and that like obviously doesn't make sense. But here I think it makes more sense. But the question is why though? Geometrically, this means that the graph of the polynomial px passes through the points 1 and does not pass through any other data points. This is sometimes referred to as a nodal interpolation problem because the polynomial must have a node, a point where it changes sign, at each of the other data points in order to satisfy the interpolation conditions. Note that in general, such a polynomial of degree n minus 1, what if you have two different polynomials that intersect at the same value of 1? Where both of those, like their x would be the same when y is 1. What happens then? I guess it's just impossible. Maybe I should ask that. Note that in general such polynomial degree n minus 1 may not exist, or it may not be unique. Whether or not such a polynomial exists and is unique on the specific set of data points and the values. Wait. Not find. No, it is not possible to find different Lagrange interpolating polynomials that have the same value for when I is 1. The Lagrange interpolation polynomial is unique for a given set of data points and is uniquely determined by the value of data points. Two polynomials have the same value of x when y is 1. This means that they must have the same value at that particular data point, and hence they must be the same polynomial. Huh? Suppose we have two polynomials that both pass through the data point and have the same value of x when y is 1. I'm not sure if I agree with this though. Because I'm just picturing in my mind if you have, like, for example, a concave and a convex function, they can both intersect at the same value, where y would be equal to 1, but they are different polynomials because they are different functions. I'm not sure if that makes sense. But since both fx and jx are Lagrange interpolating polynomials for the same set of data points, same value of y at all the other data points. Oh, let's define. Now I have. Yeah, not sure. I think I'm gonna watch a video about this. And then look for other articles as well. Maybe, so I think that is gonna be used on one of these articles here. I'm pretty sure. And I don't remember when. Yeah, here. It's probably gonna talk about it in this article, I think. And then you can do things with fast Fourier transform to make it more efficient. And I also don't remember really well how it works.
Dark mode toggle. Starks, Pardai, proofs with polynomials. 2017 November 9th. See all posts. Special thanks to Eli Ben Sasson for ongoing help, explanations, and review, coming up with some of the examples used in this post, and most crucially of all inventing a lot of this stuff. Thanks to Xiaowei Wang for review. Hopefully many people by now have heard of ZK snarks, the general-purpose succinct zero-knowledge proof technology that can be used for all sorts of USEC as ranging from verifiable computation to privacy-preserving. What you might not know is that ZK snarks have a newer, shinier cousin, ZK starks. With the T standing for transparent, ZK starks resolve one of the primary weaknesses of ZK snarks, its reliance on a trusted setup.
We are given 4 points.
They also come with much simpler cryptographic assumptions, avoiding the need for elliptic curves, pairings and the knowledge of exponent assumption, and instead relying purely on hashes and information theory. This also means that they are secure even against attackers with quantum computer. However, this comes at a cost. The size of a proof goes up from 288 bytes to a few hundred kilobytes. Sometimes the cost will not be worth it, but at other times, particularly in the context of public blockchain applications where the need for trust minimization is high, it may well, and if elliptic curves break or quantum computers do come around, it definitely will be. So how does this other kind of zero-knowledge proof work? First of all, let us review what a general-purpose succinct ZKP does. Suppose that you have a public function f, a private input x, and a public output y. You want to prove that you know an x such that f, x, equals y, without revealing what x is. Furthermore, for the proof to be succinct, you want it to be verifiable much more quickly than computing f itself. Let's go through a few examples. F is a computation that takes 2 weeks to run on a regular computer, but 2 hours on a data center. You send the data center the computation, i.e. the code to run f, the data center runs it, and gives back the answer y with the proof. You verify the proof in a few milliseconds, and are convinced that y actually is the answer. You have an encrypted transaction, of the form x1 was my old balance, x2 was your old balance, x3 is my new balance, x4 is your new balance. You want to create a proof that this transaction is valid. Specifically, old and new balances are non-negative, and the decrease in my balance cancels out the increase in your balance. X can be the pair of encryption keys, and F can be a function which contains as a built-in public input the transaction, takes as input the keys, decrypts the transaction, performs the check, and returns 1 if it passes and 0 if it does not. Y would of course be 1. You have a blockchain like Ethereum, and you download the most recent block. You want a proof that this block is valid, and that this block is at the tip of a chain where every block in the chain is valid. You ask an existing full node to provide such a proof. X is the entire blockchain, yes, all, gigabytes of it. F is a function that processes it block by block, verifies the validity and outputs the hash of the last block, and Y is the hash of the block you just download. So what's so hard about all this? As it turns out, the zero knowledge, i.e. privacy, guarantee is, relatively, easy to provide. There are a bunch of ways to convert any computation into an instance of something like the three-color graph problem, where a three-coloring of the graph corresponds to a solution of the original problem, and then use a traditional zero-knowledge proof protocol to prove that you have a valid graph coloring without revealing what it is. This excellent post by Matthew Green from 2014 describes this in some detail. The much harder thing to provide is succinctness. Intuitively speaking, proving things about computation succinctly is hard because computation is incredibly fragile. If you have a long and complex computation, and you as an evil genie have the ability to flip a 0 to a 1 anywhere in the middle of the computation, then in many cases even one flipped bit will be enough to make the computation give a completely different result. Hence, it's hard to see how you can do something like randomly sampling a computation trace in order to gauge its correctness, as it's just too easy to miss that one evil bit. However, with some fancy math, it turns out that you can. The general very high-level intuition is that the protocols that accomplish this use similar math to what is used in erasure coding, which is frequently used to make data fault-tolerant. If you have a piece of data, and you encode the data as a line, then you can pick out 4 points on the line. Any two of those 4 points are enough to reconstruct the original line, and therefore also give you the other 2 points. Furthermore, if you make even the slightest change to the data, then it is guaranteed at least 3 of those 4 points. You can also encode the data as a degree 1,000,000 polynomial, and pick out 2 million points on the polynomial. Any 1,000,001 of those points will recover the original data and therefore the other points, and any deviation in the original data will change at least 1 million points. The algorithms shown here will make heavy use of polynomials in this way for error amplification. Changing even 1 point in the original data will lead to large changes in a polynomial's trajectory. A somewhat simple example. Suppose that you want to prove that you have a polynomial p such that p, x, is an integer with 0 less than or equal to p, x, less than or equal to 9 for all x from 1 to 1 mil. This is a simple instance of the fairly common task of range checking. You might imagine this kind of check being used to verify, for example, that a set of account balances is still positive after applying some set of transaction. If it were 1 less than or equal to p, x, less than or equal to 9, this could be part of checking that the values form a correct Sudoku solution. The traditional way to prove this would be to just show all 1 million points, and verify it by checking the values. However, we want to see if we can make a proof that can be verified in less than 1 million steps. Simply randomly checking evaluations of p won't do. There's always the possibility that a malicious prover came up with a p which satisfies the constraint in 999,999 places but does not satisfy it in the last one, and random sampling only a few values will almost always miss that value. So what can we do? Let's mathematically transform the problem somewhat. Let C, x, be a constraint checking polynomial, C, x, equals 0 if 0 less than or equal to x less than or equal to 9 and is non-zero otherwise. There's a simple way to construct C, xx, x1, x2, x9. We'll assume all of our polynomials and other values use exclusively integers, so we don't need to worry about numbers in between. Now, the problem becomes, prove that you know p such that C, p, x, equals 0 for all x from 1 to 1 million. Let Z, x, equals x1, x2, x1 0 0 0 0 0 0. It's a known mathematical fact that any polynomial which equals 0 at all x from 1 to 1 million is a multiple of Z, x.
I don't know why that's the case. Ele polynomial that equals 0 at all x from 1 to a million. It's a multiple of zx. Yeah, I'm not sure if I understand that part.
Hence, the problem can now be transformed again. Prove that you know p and d such that C, p, x, equals z, x, d, x, for all x. Note that if you know a suitable C, p, x, then dividing it by z, x, to compute d, x, is not too difficult. You can use long polynomial division or more realistically a faster algorithm based on FFTs. Now, we've converted our original statement into something that looks mathematically clean and possibly quite provable. So how does one prove this? We can imagine the proof process as a three-step communication between a prover and a verifier. The prover sends some information, then the verifier sends some requests, then the prover sends some more information. First, the prover commits to, i.e. makes a Merkle tree and sends the verifier the root hash of, the evaluations of p, x, and d, x, for all x from 1 to 1 billion. Yes, billion.
Yeah, this is the stuff that I was talking about. So I think one technique is that the first number is going to be to the power 2 and the second number as well. In this case, not because they're different, so multiply, but then it's 2x, the other ones multiply by each other. So there is the pattern if the numbers are the same, where it's going to be x to the power of 2 plus 2xy plus y to the power of 2. And then because of that, you can go from this form to this form as well. I think it's factoring the name of this. I forgot the name in English. Yeah, factoring. So I think the Lagrange polynomial has probably something to do with that.
This includes the 1,000,000 points where 0 less than or equal to p, x, less than or equal to 9 as well as the
It's factoring a huge polynomial into the other one, and then getting one polynomial that is 1 in one of the points and 0 in all of the other.
We assume the verifier already knows the evaluation of z, makes a Merkle tree and sends the verifier the root hash of the evaluations of p, x, and d, x, for all x from 1 to 1. This includes the 1,000,000 points where 0 less than or equal to p, x, less than or equal to 9 as well as the 999,000,000 points where that, probably, is not the case. We assume the verifier already knows the evaluation of z, x, at all of these points. The z, x, is like a public verification key for this scheme that everyone must know ahead of time. Clients that do not have the space to store z, x, in its entirety can simply store the Merkle root of z, x, and require the prover to also provide branches for every z, x, value that the verifier needs to query. Alternatively, there are some number fields over which z, x, for certain x is very easy to calculate. After receiving the commitment, i.e., Merkle root, the verifier then selects a random 16x values between 1 and 1 billion, and asks the prover to provide the Merkle branches for p, x, and d, x. The prover provides these values, and the verifier checks that I, the branches match the Merkle root that was provided earlier, and 2, c, p, x, actually equals z, x, d, x. In all 16 cases, we know that this proves perfect completeness. If you actually know a suitable p, x, then if you calculate d, x, and construct the proof correctly, it will always pass all 16 checks. But what about soundness? That is, if a malicious prover provides a bad p, x, what is the minimum probability that they will get caught? We can analyze as follows. Because c, p, x, is a degree 10 polynomial composed with a degree 1,000,000,000 polynomial, its degree will be at most 10 million. In general, we know that two different degree n polynomials agree on at most endpoints. Hence, a degree 10,000,000,000 polynomial which is not equal to any polynomial which always equals z, x, d, x, for some x will necessarily disagree with them all at least 990 million points. Hence, the probability that a bad p, x, will get caught in even one round is already 99%. With 16 checks, the probability of getting caught goes up to 1/1032. That is to say, the scheme is about as hard to spoof as it is to compute a hash collision. So, what did we just do? We used polynomials to boost the error in any bad solution, so that any incorrect solution to the original problem, which would have required a million checks to find directly, turns into a solution to the verification protocol that can get flagged as erroneous at 99% of the time with even a single check. We can convert this three-step mechanism into a non-interactive proof, which can be broadcasted by a single prover once and then verified by anyone. Using the Fiat-Shamir heuristic, the prover first builds up a Merkle tree of the p, x, and d, x values, and computes the root hash of the tree. The root itself is then used as the source of entropy that determines what branches of the tree the prover needs to provide. The prover then broadcasts the Merkle root and the branches together as the proof. The computation is all done on the prover side, the process of computing the Merkle root from the data, and then using that to select the branches that get audited, effectively substitutes the need for an interactive verifier. The only thing a malicious prover without a valid p, x, can do is try to make a valid proof over and over again until eventually they get extremely lucky with the branches that a Merkle root that they compute selects. But with a soundness of 1/1032, probability of at least 1/1032 that a given attempted fake proof will fail the check, it would take a malicious prover billions of years to make a passable proof. Going further, to illustrate the power of this technique, let's use it to do something a little less trivial. Prove that you know the millionth Fibonacci number. To accomplish this, we'll prove that you have knowledge of a polynomial which represents a computation tape, with p, x, representing the xth Fibonacci number. The constraint checking polynomial will now hop across 3x coordinates, c, x1, x2, x3, equals x3, x2, x1. Notice how if c, p, x plus 1, p, x plus 2, equals 0 for all x, then p, x, represents a Fibonacci sequence. The translated problem becomes, prove that you know p and d such that c, p, x plus 1, p, x plus 2, equals z, x, d, x. For each of the 16 indices that the proof audits, the prover will need to provide Merkle branches for p, x plus 1, p, x plus 2, and d, x. The prover will additionally need to provide Merkle branches to show that p, 0, equals p, 1, equals 1. Otherwise, the entire process is the same. Now, to accomplish this in reality there are two problems that need to be resolved. The first problem is that if we actually try to work with regular numbers the solution would not be efficient in practice, because the numbers themselves very easily get extremely large. The millionth Fibonacci number, for example, has 208,988 digits. If we actually want to achieve succinctness in practice, instead of doing these polynomials with regular numbers, we need to use finite fields, number systems that still follow the same arithmetic laws we know and love, like a, b plus c, equals ab, plus ac, and a 2b2, equals ab, a plus b, but where each number is guaranteed to take up a constant amount of space. Proving claims about the
Yeah, this is the stuff that I was talking about. And now he's gonna talk about modular, because we want to reduce the field to integers. And that's where it starts getting very confusing. The other stuff is understandable, but I just don't know. Like, there is probably some proof that of this stuff that I was talking about before, where one polynomial is going to be a multiple of the other one. I just don't know that's why that is the case. I think it's here. Yeah, it's a known mathematical fact that any polynomial which equals 0 at all x from 1 to is a multiple of... I don't understand this thing here. Is it saying that all of the values like is gonna be just the x coordinates there? Because all the values of x are equal to 0 from 1 to 1 million. And that is a multiple. If that's the case, then I think it makes sense. Because it's like making everything equal to 1, so obviously it's going to be multiple of the other polynomial. But I don't understand this very well. The rest is kind of intuitive to understand, I think. But I don't understand very well. Like, I understand that it's using the hash of the tree, the Merkle tree, to find points on the polynomial, and then and this is a very similar pattern that I've seen from other hash algorithms so far. Like they all seem to use these points. Like all of them involve selecting different points and then on some equation, and then using those points of the equation to create secret messages between the two people based on a mathematical property that allows both people to only unlock the messages with the two values that they have. And here I think it's the same thing, where you have these two polynomials, and then based on the points of these polynomials and using the hash function of the tree, you can verify the message, but you can't compute the polynomial, I think. Something like that. But I don't understand really well. It's gonna take more time to understand. But I'm gonna come back to this probably multiple times. Like the reason why I'm reading now is because after I write these articles and then I'll go write the articles about algorithms. I'm obviously gonna study this more. Then when I come back, like I'm gonna have already a decent understanding, so it's gonna be easier to. And also I wanna start building things eventually. So I think it's better to have like the exposure, even though I don't understand really well, because then I'm already very familiar and it's easier. It gets easier and easier each time to understand.
Fibonacci number would then require a more complicated design that implements big number arithmetic on top of this finite field map. The simplest possible finite field is modular arithmetic. That is, replace every instance of a plus b with a plus b mod n for some prime n. Do the same for subtraction and multiplication. And for division use modular inverses. If n equals 7, then 3 plus 4 equals 0, 2 plus 6 equals 1, 3 4 equals 5, 4 slash 2 equals 2, and 5 slash 2 equals 6. You can learn more about these kinds of numbers.
Modular inverse is the thing that I just talked about in the extended Euclidean algorithm, where you wanna get the remainder equal to 1, I think. And you can't simply divide because it's different with modular arithmetic. Yeah, modular inverse is when the x, a times x is equal to 1 mod m. So it's like the division of modular arithmetic. And it's very confusing to understand why.
From my description on prime fields here, search prime field in the page, or this Wikipedia article on modular arithmetic. The articles that you'll find by searching directly for finite fields and prime fields unfortunately tend to be very complicated and go straight into abstract algebra. Don't bother with those. Second, you might have noticed that in my above proof sketch for soundness I neglected to cover one kind of attack. What if, instead of a plausible degree 1,000,000 p x and degree 9,000,000 d x, the attacker commits to some values that are not on any such relatively low degree polynomial, then the argument that an invalid c p x must differ from any valid c p x on at least 990 million points does not apply, and so different and much more effective kinds of attacks are possible. For example, an attacker could generate a random value p for every x, then compute d equals c p slash z x, and commit to these values in place of p x and d x. These values would not be on any kind of low degree polynomial, but they would pass the test. It turns out that this possibility can be effectively defended against, though the tools for doing so are fairly complex, and so you can quite legitimately say that they make up the bulk of the mathematical innovation in STAR. Also, the solution has a limitation. You can weed out commitments to data that are very far from any degree 1,000,000 polynomial, e.g. you would need to change 20% of all the values to make it a degree 1,000,000 polynomial, but you cannot weed out commitments to data that only differ from a polynomial in only one or two coordinate. Hence, what these tools will provide is proof of proximity, proof that most of the points on P and D correspond to the right kind of polynomial. As it turns out, this is sufficient to make a proof, though there are two catches.
And so I think what is happening is using the polynomial to verify the points. So the polynomial is kind of like the secret key, I think, a private key. Well, the polynomial would be the public key, and then the points would be the private, I think. Something like that.
As it turns out, this is sufficient to make a proof, though there are two catches. First, the verifier needs to check a few more indices to make up for the additional room for error that this limitation introduces. Second, if we are doing boundary constraint checking, verifying P0 equals P1 equals 1 in the Fibonacci example above, then we need to extend the proof of proximity to not only prove that most points are on the same polynomial, but also prove that those two specific points, or whatever other number of specific points you want to check, are on that polynomial. In the next part of this series, I will describe the solution to proximity checking in much more detail, and in the third part I will describe how more complex constraint functions can be constructed to check not just Fibonacci numbers and ranges, but also arbitrary computation.
I'm probably not going to change much as well of this article here. I think I'm just gonna, because I think that everything is correct based on the stuff that I already saw. I know that it's correct based on the stuff that I already saw, but I don't understand really well how it works. Like now I think that this stuff about the points I clarified, so I understand now. But it's still kind of confusing to me, like why this division here and how it works. So I'm just gonna try to clarify that, but I think the stuff that is written here is correct. So, and the algorithm is relatively easy to understand. Like it's just it's similar to one of the graph algorithms that I saw in the past. I don't remember which one. That it uses this list to map values on the main list with the points. And then it updates the values according to I think the graph algorithm is one that uses Floyd-Marshall. Like it updates the weights first so that it removes the negatives. Then it does a search like a Jastrow or Bellman-Ford or Floyd-Marshall, I think, to find the shortest path. And then after that, it updates the weights again. And in that algorithm, it uses a similar technique that they are using here. And then these values of L are going to be the updated values of this equation here. And then you're going to multiply this by y, which is probably the values that are passed for y here. And this is going to be the final polynomial that it returns. So it's not difficult to understand this algorithm here. But I want to obviously understand more how it works. Like, why does it divide here? I think that's the main thing that I want to clarify. And -1. This is slightly confusing to me because of the stuff that I talked about, where you can have a concave and convex function, and they both have the same value of y when x equals 1. No, actually the other way around. When y equals 1, they have the same value of x. But the functions are different. So in this case, like I assume that you wouldn't be able to find the Lagrange interpolation. But also, that doesn't make a lot of sense to me. And I don't understand why this row here, where it can only be the value of the value of x can only be 1 once for all the polynomials in order to find the Lagrange interpolation. So this thing that I want to understand more, and then why you're dividing. I think this one I'm going to close now. I'm going to read this in the future probably again to understand more. And I'm going to read these other ones here. I think I'm going to watch the videos first.
Lagrange Interpolation, Trevor Ross-Hero, Lurkurzer, Patrick Korn, and 7 others. The Lagrange interpolation formula is a way to find a polynomial which takes on certain values at arbitrary points. Specifically, it gives a constructive proof of the theorem. Suppose we have 1 point, 1, 3. How can we find a polynomial that could represent it? P x equals 3, P x equals 3, P x equals 3, P 1 equals 3, P 1 equals 3, P 1 equals 3. Suppose we have sequence of points 1, 3, 2, 4. How can we find a polynomial that could represent it? P x equals x2, 1, 2 times 3 plus x1, 2, 1 times 4. P x equals backslash frac x 2, 1 to 2 backslash times 3 plus backslash frac x 1, 2 to 1 backslash times 4. P x equals 1, 2 x2 times 3 plus 2, 1 x1 times 4. P 1 equals 3 P 2 equals 4 P 1 equals 3 backslash P 2 equals 4. P 1 equals 3 P 2 equals 4. Suppose we have sequence of points 1, 3, 2, 4, 7, 11. How can we find a polynomial that could represent it? P x equals x2, x7, 1, 2, 1, 7.
Like this is the equation here is just translating the set of points into this equation, and then it's gonna generalize here. Like I get this, but I don't understand why you can represent the polynomial using the points. That's the thing. But I guess it's just like some mathematical observation, let's say. But I don't know, like, how can I search for this? There's more stuff here.
Times 3 plus x1, x7, 2, 1, 2, 7 times 4 plus x1, x2, 7, 1, 7, 2 times 11. P x equals backslash frac x2, x7, 1 to 2, 1 to 7 backslash times 3 plus backslash frac x1, x7, 2 to 1, 2 to 7 backslash times 4 plus backslash frac x1, x2, 7 to 1, 7 to 2 backslash times 11. P x equals 1, 2, 1, 7 x2, x7 times 3 plus 2, 1, 2, 7 x1, x7 times 4 plus 7, 1, 7, 2 x1, x2 times 11. P 1 equals 3 P 2 equals 4 P 7 equals.
So the quotient is always equal to y here, I think. And it's 3, 4, 11. And here is equal to, here I don't understand. So it's 2 and 7 actually. So it's getting the x points of both of the other ones, and this is the, yeah, it's like it says here. But it always gets x1 unless it's the first element. And the other ones increase, I think. Yeah, the only ones that increase are this one on the left and these other ones on the right. And the rest is always x1. Except for this one, which is the first one.
Theorem. Given backslash text deg P. Theorem. Given n and distinct real values x1, x2, xn x underscore 1, x underscore 2, backslash l dots, x underscore n x1, x2, xn and n real values y1, y2, yn y underscore 1, y underscore 2, backslash l dots, y underscore New York 1, y2, yn, not necessarily distinct. There is a unique polynomial PPP with real coefficients satisfying P, 11, equals yp, x underscore I, equals y underscore ip, 11, equals y for I set membership symbol 1, 2, and this theorem can be viewed as a generalization of the well-known fact that 2 points uniquely determine a straight line, 3 points uniquely determine the graph of a quadratic polynomial, 4 points uniquely determine the graph of a cubic polynomial, and so on. 2 caveats. 1. The points are required to have different triple x coordinates, and 2. The quadratic polynomial might actually be a linear or constant polynomial, the cubic polynomial might actually be a quadratic, linear, or constant polynomial, and so on. Proof. First, a proof that the polynomial PPP is unique. Suppose QQQ and RRR are polynomials with the above properties. Then QRQRQR vanishes on x1, x2, xn, x underscore 1, x underscore 2 backslash l dots x underscore n x1, x2, xn, but its degree is less than n. Then QRQRQR vanishes on x1, x2, xn, and n. A non-zero q equals r q equals r dot q equals r q equals r, a non-zero polynomial of degree. Q equals r q equals r dot q equals r. Now, to show that PPP exists, let P1 x equals xx2 x P underscore 1 P1 x equals x1 x2 x1 x3 x1 xn xx2 xx3 xxn. Then P1 x1 equals 1 P underscore 1 x underscore 1 equals 1 P1 x1 equals 1 and P1 x2 equals P1 x3 equals P1 xn equals 0. P underscore 1 x underscore 2 equals P underscore 1 x underscore 3 equals backslash dots equals P underscore 1 x underscore n equals 0. P1 x2 equals P1 x3 equals P1 xn equals 0. Then p x equals sigma e pi x p x equals backslash sum y underscore ip underscore I x p x equals sigma e pi x is a polynomial with real coefficients satisfying p.
Maybe we should search for Lagrange interpolation proof. I'll watch this video first.
Points, and we need to fit a function that passes through these 4 points. The idea behind a Lagrange interpolation is the following. Create a polynomial for each point such that it passes through that point and is 0 at all other points. Finally, add all these polynomials to obtain the interpolation polynomial. So let's see how to do this. Let's begin at the first point. The function must be 0 at all the given points. So there must be factors of a polynomial, which means multiplying x minus the x coordinates will give us a polynomial that's 0 at these points. That was easy, but it doesn't pass through the given point yet. One simple way to force a function to do this is to divide the function by the y value at the y point. In our case, the y value at the first point is minus 17.5. So dividing by minus 17.5, we can make the function value 1 at x is equal to 0. What we have done essentially is substituted x is equal to 0 in f1 and divided it. Note, it still does not pass through the given point, but we just need to multiply by the required y value, which is 3 in our case, to fix it. So till now, we have tailored one function that passes through the given point and is 0 at all other points. Repeating the same thing for remaining 3 points, we would have all 4 functions ready. Finally, add them up to obtain the interpolation. Thank you, and do consider subscribing. Thank you, and do consider add them up to obtain the interpolation.
That's a very good video. It's a lot easier to understand now, but I'm gonna search more, obviously. I was picturing the wrong way, now I understand. So you're not finding one polynomial, you're finding multiple ones, and then you're adding them together. That's the thing. And each one of them, the polynomials, is gonna be 0 on all of the other ones, and it's gonna be 1 on the one that is on the respective point, I think. And let me watch this again. Thinking about if there's a way to change this stuff here, or it's gonna be easier to understand. And now I understand. Because the way that I think I was confusing because I had machine learning stuff on my mind, but it's not the same thing. I was thinking about constructing one polynomial, like essentially that's what it achieves, but it achieves in a different way. It constructs one polynomial based on the data points, but I was thinking about it in a different way. And then you build the polynomial by adding together. And you multiply by y so that it passes the point, I think. So it crosses the point on the data. Yeah, now it's very, very clear actually to me. I think I'm gonna recommend this video. Maybe I can embed the video. I think I'm trying to think if I embedded a video in the past in the blog. I think I'm gonna have to see this now, actually. because if I'm gonna embed the YouTube video, I need a component. Yes, I'm passing embed. How does it work? I think I just pass embed and then the href. Problem is I don't remember which article I used this. Maybe I should post a link. Oh, actually, let me think. I guess. Do I use that? Maybe I'll use the source link. Hmm. I think I'm gonna do the easy one. Just this one. After I finish these articles here, I think I'm gonna like open the blog and then go over all the articles and fix the intro links that I have for each thing. And also check all of these links here if they are working or not. There's also some stuff that I need to finish about the privacy policy and things like that. So I think I'm gonna do those things after I finish these articles here. And then I'm gonna go back to doing the articles about algorithms. Let me already opens. The thing that maybe is better if I check this stuff now, because the problem is that if I put a bunch of articles, then I might get a bug there, and then it's gonna be hard to know from which article the bug's coming from. But I think it's not that big of a deal because most of the articles are the same way. Like I'm very confident that there won't be bugs on them because I'm not doing anything different than I did with the previous articles that I already have. So if there is a bug, it's probably going to be on this excerpt here, and it will be easy to fix, I think. Change this. And then to share, you need to get the embed version here. And the only downside of putting this video here is because it's not my channel, so there's a chance that he removes the thing. But it's not that big of a deal, I think.
We are given 4 points, and we need to fit a function that passes through these 4 points. The idea behind a Lagrange interpolation is the following. Create a polynomial for each point such that it passes through that point and is 0 at all other points. Finally, add all such polynomials to obtain the interpolation polynomial. So let's add such polynomials.
Oh, I think I get it now. So it's gonna be 0 at all the other points of the data sets. The polynomial is gonna be 0. It's not gonna be 0 on all of the points of the polynomial. It's just gonna be 0 at the points of the data sets that are not. So it's 1 on that polynomial. That's why I was confused. But now I think I get it. It's 1 on the polynomial itself, and on the point of the polynomial itself, and 0 on all of the other points that are not part of the polynomial. Yeah, but here it's still weird because like it's not gonna be 1 here.
Finally, add all such polynomials to obtain the interpolation polynomial. So let's see how to do this. Let's begin at the first point. The function must be 0 at all other given points. So they must be factors of a polynomial, which means multiplying x minus the x coordinates will give us a polynomial that's 0 at these points. That was easy, but it doesn't pass through the given point yet. One simple way to force the function to do this.
Oh, I get it, because you're constructing the polynomial based on where it's gonna be 0. So is that the stuff that I thought about before, where I said about the factoring thing, where you get the points that are gonna be 0 based on the multiplication, because then you know when x is equal to the factor of the other points, then it means that it is 0. So that makes a lot of sense.
Is to divide the function by the y value at the required point. In our case, the y value at the first point is minus 17.5. So dividing by minus 17.5, we can make the function value 1 at x is equal to 0. What we have done essentially is substituted x
I
is
think
equal
this guy's probably using the Manning, I think, is the library from 3 Blue, 1 Brown. A very good video. It's probably the best video that I found about this, actually.
to 0 in f1 and divided it. Note, it still does not pass through the given point, but we just need to multiply by the required y value, which is 3 in our case, to fix it. So till now, we have tailored one function that passes minus 17.5. It doesn't pass through the given point yet. One simple way to force the function to do this is to divide the function by the y value at the required point. In our case, the y value at the first point is minus 17.5. So dividing by minus 7.
This part I don't understand. Because that value is going to be arbitrary depending on the other points. I don't get it.
17.5, we can make the function value 1 at x is equal to 0.
Maybe, yes, x is going to be 0, so. But it's still, I don't know.
What we have done essentially is substituted x is equal to 0 in f1 and divided it. Note, it still does not pass through the given point, but we just need to multiply by the required y value, which is 3 in our case, to fix it.
Oh, now it makes sense. So you're just getting 0 minus the other values of the other points. Multiplying them, and then you multiply by the value of the point itself.
So till now, we have tailored one function that passes through the given point and is 0 at all other points. Repeating the same thing for remaining 3 points, we would have all 4 functions ready. Finally, add them up to obtain the interpolation. Thank you, and do consider
Very good
subscribing.
video. I think I'm gonna stop here. I'm probably not gonna modify this much. I think I understand how it works. The algorithm is not that difficult to understand as well. A lot easier than the previous one. And based on the stuff that I read here, I think it's correct. Everything seems to be correct. So now I'm just gonna test this on the blog, I think. I think I'm gonna do that now, actually. Let's get that over with and then move on to the other stuff. I was actually on blockchain. My concern here is that when I have a bunch of articles, if it's gonna slow down too much. Hopefully not. And if it does, I'm gonna have to think about the algorithms again on how to optimize this. Like how to cache values and maybe hopefully there is some way to make this faster on Next.js. So it's not working. Mm. I know I don't need to import on this file because I'm passing through here, but I don't understand why it's not working. If I pass href instead. I guess I could just look at the TMUI documentation. Yeah, it is source. But why is not working? Oh, it's because it might be, they might be different. Yeah. So I think I updated this file, but I didn't update it on the other ones. Hmm. Let me. And now I don't know. I don't remember really well. I think. Let me think. It's probably better to copy the programming one and then post that. Because I think the last time that I modified this was when I was having problem with the navigation. So I think I changed the navigation here as well. Let me think. It seems to be the same. So do I just add the embed there, or do I copy everything? I think I'm gonna copy everything. Just updates and then it's probably gonna work. Yeah, nice. I wonder if I put. Yeah. So I'm gonna change the style there, but I'm not gonna do that anymore. So that the letter is different. The color of the link for the channel is different, but I don't think I'm gonna do that. Actually, let me think. No, whatever. Oh, that's another thing that I always forget. I'm gonna have to check this on all the articles as well, where you have to escape these characters, and some of them I escaped, and I'm not really sure, like, if it is gonna show the escape character or not. And it looks like it's not showing here. Yeah. There are other ones also when they put the multiplication without wrapping the code. Then you can change the color there and do like something that it wasn't intended. And the rest seems to be fine, I think. I think maybe in the future I should incorporate images as well, probably. And once I make the videos as well, it might be a good idea to put the videos on each one of them. Yeah, these links I have to fix as well. But I don't have the article yet about proposer builder separation. Yeah, maybe it is better to. Yeah, but the thing is, I feel like a lot of them, like I post the interlink, but I still don't have the article, so that's the problem. And the thing is, proposer builder separation is gonna be difficult to write about, I think, because I have to cover all of these topics before. To after this, there's also data availability sampling, and it's gonna be really hard to explain the how it works and the mathematics there. And maybe it's fine if I leave some of them without the link for now. But I should probably, after I finish this articles here, I should probably go on all of the ones that I did so far to see if there are any missing links. But I think I'm gonna stop here. I'm gonna watch these videos probably from this guy. And I might, yeah, I'm not really sure what I'm gonna do. But if I don't do these articles here off stream, I might come back today, honestly. Like depends on, yeah, depends on what I decide to do. But I'll probably come back tomorrow and I'll continue to do these articles here. These ones about this stuff and the articles about the algorithms. So if I don't come back today, probably, actually probably Friday, very likely Friday, and maybe tomorrow I'll come back. So